Okay, so as Paul mentioned, I'm going to be talking about Tipkit, which is a new framework from Apple they announced this year. It's a relatively straightforward framework. I haven't dived into the code too much, so I don't have any demos or anything, but I will give you like a little overview of how we can use it to improve your apps. So what is Tipkit? It's a simple Apple framework that makes it easy to show your users educational messaging. That can be things like new features, maybe hidden features that users may not know about, or simple things like that. Hidden ones, or even more efficient ways to accomplish a task. Those are the kinds of examples where you'd want to use Tipkit. Some more examples, like this, expressing yourself with reactions. So this is like a new feature in iMessage that you might want users to learn about, or sending a quick response. Things that you would not want to use it for are promotional messaging, or error messaging, or things that are just not actionable. You don't want to give people random information. It has to be timely and actionable. And you also want to make sure they're very to the point and not very lengthy, like this last one here. So how do we make a tip? It's relatively straightforward. You just define this tip protocol where you supply a title, a message, and an optional asset. Like I said before, they're most useful when the titles are direct action phrases. You want them to state the feature, and the message should contain benefits or instructions. Users should know why they'd want to use the feature and accomplish the task later on. How do we display the tip? So it's a simple SwiftUI view. Up here we've defined our tip protocol. We've supplied a title, a message, and this asset. And down here we've defined our tip view, where we then supply that tip and an arrow edge. And I'll point to what this arrow edge is later on. Okay. Some more visuals here on defining your tip and showing it on the UI. Here we have a standard SwiftUI button, and we can define our tip here using this modifier. And what this will do is essentially show this tip on this button. And this is that arrow edge here that we can, it's hard to see over here, but we can sort of define where this arrow edge appears. And iOS will take care of making sure it's not clipped by the window and appears in the right place in the UI. One more thing that we can actually do is apply actions. So as you can see over here, within our original tip protocol, we can define an action which takes an ID, a title, and it's not shown here, but you can also supply a function. So you can respond to user behavior when they tap on that tip. Okay, so eligibility rules. At the heart of Tipkit is rules, which basically determine what conditions you want users to see your tips for. You obviously don't want them to see a tip every time. You might want them to see it maybe once a day. Or if rules are being met to see them, you don't want them to see them, every day or 100 times a week. So on the left here, we have these properties that you can define using this tag called a parameter. And you can also define a set of rules. And each of these rules use macros, which some of you may or may not be familiar with in Swift. But a simple example here is this is logged in rule. And by supplying these rules to my tip here, I can basically tell the system a list of conditions that need to be met in order to show the tip to the user. And how we connect these rules to the tip is using this donation here. And this will basically tell it to sort of run through the rules list before showing the tip. Another kind of filter that you can use on the rules is using like time-based rules. So in this example, a user has entered any backguard detail view at least 3 times in the last 5 days. So that might be something important based on your app. There's some additional configurations that are useful. For example, there's the tip center. I believe it's now been renamed to tips because a lot of this content came from the original WWDC talk, and I have not dived into the beta code. things like display frequencies. You could have daily, hourly, you could have something custom. Essentially what this does is, let's say you have 20 different tips in your app, which is possible for an app like ours. We don't want a user seeing, 10 different tips in a day. So this sort of serves as like an override and allows you to create some kind of control over how much information you're giving your user. Another thing you can do is to set this options array, also in the same tip protocol I talked about. You might have some important tips that you want users to see no matter what. And so you can apply this ignores display frequency attribute to your tip. Finally, when people see tips, you probably don't want them to see it again. So you would call this invalidate method on your tip object. And the only reason I'm familiar with is user performed action, but I imagine there could be more over time. So you can organize what tips users have seen and which ones you don't want them to see anymore. You have additional options like max display count. And something important here actually is testing your tips. So let's say you have 40 or 50 tips in your app. You don't want all of them to appear. So if you're trying to just test your tips, you have some helpers here, like showing all the tips in the app, doing specific tips, hiding specific tips, and then resetting all your data. So all the rules I talked about, all the conditions that need to be met, you can kind of start over from there. Okay, moving on. So I kind of touched on this here and there, but this was more designed for my presentation internally, which is how we could use Tipkit, and it might give you some ideas as well. For us, I own the account opening flow at Capital One, and so we see over 3,000 accounts opened every day, and that doesn't include how many more thousands of users come into the flow and probably don't open an account because they're confused or don't really know how to finish things quickly. So there's a lot of use cases for making it easy for users to understand what's happening in the flow and complete it quickly. And this can go beyond just our flow. As an example here, this pair move tab may not make a lot of sense to a user off the bat, but with the tip kit, with the tip, we could easily bring them into the feature and have them use things they otherwise might not have. A little caveat that I'm still learning about is it's not clear how much the UI is customizable. So depending on your app's design language, you may or may not be able to really integrate it with your entire UI, but that is TBD. Some resources that I use, TechCrunch article, and of course some Apple documentation. Yeah, that's it. Sure.
Hi, Alex Brown. What's the voiceover experience like this?
I have not happened to research that or look into it, but I imagine it would work similarly to having accessibility identifier set on that view. One thing I learned today is that you can use UI kit wrappers for the SwiftUI view. So if you're familiar with using accessibility with UI kit, my guess is that it might work similar to that.
Thank you. Yeah. Have you done any studies, or are there any studies about like before and after using Tipkit, the improvement in feature discovery or funneling?
That's a good question. Like I had mentioned before, like we haven't had a chance to really experiment. I think the code for this only came out with the most recent beta, like 5, I think, with Xcode 15. But I'm definitely excited to like try it out with our flow and see how it works.
There you go. Thanks. This feature is presumably iOS 17. Of course, you might have an app which needs to deploy to iOS 16 as well. As it's a view modifier, how would you recommend we use this in an app which needs to deploy to 16 and 17?
That's a good question. I honestly don't have an answer. Yeah, I'd love to get back to you on that one. Yeah.
A quick question. The examples you showed were in Swift, but there's no reason we wouldn't be able to use this in Objective-C.
I don't know if there's an Objective-C API for it. Yeah, there might just be SwiftUI and UI kit. All right, if no one else has more questions, call it a day. Thanks for listening.
Yeah, thanks for making this possible. Hard work, but we're all here. This is awesome. My talk is called "A Day in the Life of a SwiftUI View," and I want to talk really about the mental model that I've built up for SwiftUI. As everybody who's done SwiftUI like it's not always that easy, and you never really know why and what you're doing wrong, and like it takes quite some time to build up this mental model for how things work and like how you should be doing things. And even then, you still make mistakes. At least I do. And I learned these things that I want to present. I learned these through a bunch of different ways. So one is by writing a book about it. Another one is by teaching workshops, and like all of that feedback sort of really helped me understand things. And yeah, that's what I'm going to share. So just to be clear about this, I don't know how SwiftUI actually works under the hood. Like nobody except the people at Apple do, or the people who have been at Apple. Like I don't know, but I think I've got a good understanding. And one more sort of thing I'll add to that is I learned also a lot of this by re-implementing stuff. So we re-implemented the layout system that SwiftUI has as closely as we could, and I think we got very close, and also the state system. And those are also the two topics we'll cover today mainly. And what we'll talk about is when we take some code, this gets turned into trees. I call these view trees, and then these trees get turned into the attribute graph. I like to call this the render tree. So we're going to be mainly focusing on those three things. Let's see if the clicker works. It's been a while. Yes. So this is the view we're going to be writing. We're going to be writing a simple content view, and actually we will be writing our own version of my async or of async image. I called it my async image, and we're going to start loading that URL. And the first thing to notice is when you have a view like this, what SwiftUI will do is it will create a node in the render tree. Or the attribute graph. And that's what you can see here. This is the node that SwiftUI creates. And the render tree is not something we ever deal with directly. We have no access to this or the attribute graph. There's no way we can directly access it, but I think it's essential to understand how this works and what's happening in order to be effective for SwiftUI. Now, SwiftUI creates that node, and then the next thing it knows to do is that it needs to expand the body of that view. And to do that, it needs to just run this body computed property. So that's what it does. And then it constructs a view tree. And in this case, the view tree has a single node, my async image, and it has that URL property for us. And now is sort of the essential part. So render trees, they're persistent. They stay around. You can think of these really almost like UI views or NS views. Like these are almost like objects. How they actually work, I don't know, but these are similar to objects. They stay around for as long as your view is around. Whereas the view tree in the middle, they are ephemeral. They go away immediately. Like your render tree will get constructed from the view tree, and then the view tree is discarded. So these are struct values that have a very short lifetime, whereas the render tree has a long lifetime. So this is what happens. SwiftUI takes that view tree and adds it to the render tree. So very basic so far, right? And now it will discard the view tree and that code, and it's done with rendering, right? And now it needs to expand the body of my async image. So that's the next step that happens. And I created a very simple sort of skeleton here. It has only the URL property and an empty body. And the first thing we'll do is, because we need to start loading data here, is that we'll create a state property. And that looks like this. And we initialize it with nil. Now, what happens, I think is very interesting. This state property does not live in the view tree. It lives in the render tree. And whenever we write a state property in a view, SwiftUI will allocate memory for that in the render tree. So here we have this image data property. The other thing that SwiftUI does, it uses this initial value that we provided on line 2. I don't know if you can see the line numbers. We said equals nil. That's how the value that SwiftUI uses to initialize the memory in the render tree. After that, we can assign all the initial values we want, like pass it in from the outside. It's not going to have any effect. This nil is only used once, only when the node in the render tree gets created. And if we want to change the state property, we can only do so from the body of our views. And that's something to keep in mind. Now, how do we write the body of our view? Well, the simplest thing we could do is something like this, right? We just write an image and force unwrap everything. And of course, this doesn't work, but if we would do so, This would be your view tree. Now, we need to wrap this image a little bit. We need to at least check that we have data and that we can successfully create an NS image out of this. So that's the next step. We add an if-let around it. So if we have the data, if we can turn it into an image, then we actually display it. Otherwise, we do a progress view. And the effect this has on the view tree, I think, is very interesting. So this shows us, or this gives us a conditional content with 2 children. Actually, there's only 1 child, the progress view. But if you look at the type of this body, you'll see that if you can print this, if you look at the type of this body, you'll see that there's a conditional content that SwiftUI knows there's going to be either an image or a progress view. Never neither, never both. And I think, which it's not really the point for today, but this is one of the reasons why SwiftUI can be so efficient. It doesn't need to do full diffing. It just knows like, okay, here's something that can change. I need to take care of that, but it will never display like a text or a color or whatever. It will always be either an image or a progress view. Okay, so now we need to start loading the data. And there's a bunch of ways we can do this. So one way you might want to do this is by loading the data in onAppear. So I added an OS log here, and imagine that would load the data. We'll actually load the data later on, but imagine that would do so. So if we had that, and we would put our async image, which has the progress view, we would put it in a view that has, you know, like let's say a text view is there as well. Now, if I start typing, you can see that this log very quickly expands. And what's happening is every time our parent view, the content view, is has a changed text, it will re-execute its body. Every time the body gets re-executed, it constructs a new myasync image view. So the init is not the place to do this. Never do anything expensive in the init. If you take one thing away from this talk, and you can leave if you want to. If you take one thing away from this talk, do not do anything expensive in init. Do not load data in init, and do not use like create state objects and stuff like that, which is also a very popular thing because inits should be extremely cheap. And you can test it out by just putting your view inside another view with something like a text field. Okay, let's continue. So this is wrong. Do not do this. Now, what do we do instead? Well, we have to use something like onAppear. Focus here again. Clicker stopped working. That's okay. We have to use something like onAppear. So let's go back to what we had before and add an onAppear. Well, actually, if we try to type that, it doesn't work. It doesn't compile because we have an if-else here, and you cannot write an onAppear on top of an if-else. That's a little bit unfortunate. So we have to wrap our view. So I'll just add a Z stack or a Z stack, I guess. It doesn't really matter what you use, what kind of container, but you have to wrap it in some way. And then you can do the onAppear. And in this case, the Z stack doesn't do anything except for providing a wrapper. It has no other effect. What's interesting is, of course, that once we add that Z stack, it adds a new parent node to our tree. And you always, I think it's always very important to keep in mind, like when I write a modifier or a view, what does this do to the tree? How does this modify the tree? That's Z stack, and now we can add our onAppear. So do it on top of the Z stack. And what's again very interesting is that this onAppear is now the new root node of our view tree, which is maybe a little bit unexpected, but if you think of it, it kind of makes sense, right? Like the onAppear happens basically outside of the Z stack. And again, what you can do is if you don't believe me, you can take this code, type it into Xcode, and then print the type of the body of that view, and you will see this hierarchy. It's a little bit, it's not as nicely laid out as the tree here. It's like a big type with all kinds of nesting, but you can see the exact hierarchy that SwiftUI creates. Okay, so we're almost done with at least the first approach, right? Like we have our onAppear. The problem is I am giving a presentation and I want the code to fit nicely on the slides, and so I would like to use async await, which doesn't play well with onAppear, or at least it works better with task. So I'm going to change that to task, and now we can load all the image data in a single line, which is nice, at least for slides. And that changes our view tree slightly. So instead of the on appear, we now have the task. I think we're done. Let's have a look. Okay, so now we have constructed this view tree, and we can take it and turn it into a render tree. And what SwiftUI will do, it will actually just one-to-one copy this and add these nodes. So you can see here, there's a task node here, and a Z stack, and a Z stack, and a conditional content, and a conditional content, and a progress view, and a progress view. So these are like, this is a one-to-one copy. There's a little bit more that's going on. So we can get rid of that view tree. And the other thing that's going on is that SwiftUI will of course need to keep track for on appear or for the task whether or not the closure executed, because we really only want to execute it when the view first appears, not every single time our init runs or a body runs, because we just saw that's way too often. So what SwiftUI will do internally, it has this something like a Boolean did appear. I'm pretty sure this is not how they implemented it, but for the model, this is sort of what happens. It has the did appear equals false as the initial value, and then when the view appears on screen, it starts executing that task for us, sets the Boolean to true, and then it will never run again. Let's see if that actually works. So you can, it's a little bit hard to see, but it did appear now changed to true. We have at the bottom here, we have this little task that got created. It starts loading the data, and once it's done, it updates our image data property. Anytime any property changes in the render tree in a node, SwiftUI will invalidate that node. So in this case, the image data property, which is a state property, got changed, but also if the URL changes, SwiftUI will invalidate that node. So that means that all these nodes become gray, and SwiftUI knows to re-execute the body. It's important here that these nodes become gray, but they do not go away. This is the render tree. These nodes are persistent, they stay around. So what SwiftUI will do is says, okay, I have this image data, this is the code we had before, so let me just re-execute that body for you. And you can see this is almost the same view tree. We still have our tasks, our Z-stack, and the conditional content. But in the view tree, we can see there's now an image node, whereas in the render tree, we have a progress view. And this is really cool about SwiftUI. It will just, take care of this for us. In UIKit or in AppKit, you need to remove the old subview and insert the new one. In SwiftUI, this happens for us. Like this is done completely automatically. So SwiftUI will actually remove that progress view and insert the image. And these are both called transitions. So there's a removal transition for the progress view if you animate it, and an insertion for the image view if you animate it. And most of the time, transitions happen at the same time, so it looks like the progress view fades into the image. Okay, so let's have a look. So our render tree is now updated. Now it has the image, and SwiftUI can basically discard our view tree, and it's done. And I think now we should have a working implementation. So you just saw the progress spinner and the logo popped up. So all is good, right? Did anybody see a problem already? Not yet. Okay, this is great. So this is the problem. Like we have been working now with this sort of imperative on appear task, which is sort of an imperative escape hatch. And anytime you work with that, you need to be super careful, because you might write a view that seems like it works, as we just did, but it's broken. And I'll show you. So let's modify our content view to show this problem. So this is what we had before, just a single image. And I'm going to add a state property. Initially, it'll be true, just to flip between two images. And then I'm going to wrap my image in a VStack, and I'm going to add a button that toggles this state property. And depending on the condition, we either show a logo or a photo. So let's see if this works. We get the following view tree out. This is what we expected. And we get a render tree. And note that this state property turned into memory in the render tree. And so we're good. And if the condition changes, so I don't know if you noticed, but initially it was true. If the condition changes to false, the a body will get invalidated because a property changed, and SwiftUI will re-execute. You can see here it's still logo.png. In the render tree, it will re-execute to the photo.jpg. And like this seems to work so far, right? Like SwiftUI will update our render tree from the view tree. And now the myasync image is invalid because we have this changed property. We had logo.png, now we have photo.jpg. So that's the next step. So let's see, just check what happens if we tap this button. So tap it, nothing happens, and we can tap it as often as we want. I tried this, it doesn't work. So we need something better there. This is the render tree we ended up with for our myasync image. It's a lot to unpack, but we had the image with the data, with the logo data. We have the task that had already appeared, the Z stack of conditional content, and the image for the logo. And remember, this image data is 8,000 bytes. That's the bytes for displaying the logo. Because the URL changed, our image is now invalid and the whole subtree is invalid. So SwiftUI needs to re-execute the body. This is the code we wrote before. And this is the newly executed view tree, the newly constructed view tree. So this looks exactly like what we had before. And this is the render tree. Now the problem lies in our task. The did appear is set to true. What we really wanted is whenever this URL changes, we want to start loading that data. But the task had already appeared. So it's not going to load the data for us. The task has already appeared. The data will never be loaded. Like it will construct a new view tree, but it's exactly the same as the old view tree. And this is a problem, right? Like we need to fix this. And I think it's extra problematic because at first, when we wrote the view, it seemed to work. So be very aware of this. So how do we fix this? Oh yeah, let me just point out why this is a problem and how you can spot this during code reviews, either if it's your own code or coworkers. The problem is actually here, this URL property. This is a dependency inside our task. We have a dependency on the URL property of our view. When this URL changes, we want to run our task again. We want to, keep track of the dependency, and SwiftUI doesn't do so for us automatically. Whenever the URL changes, it executes the body again. It's not going to re-execute that task. Okay, so we'll explore a few solutions to fix this. Let's go for the brute force solution first. And that's adding an identity. So I added the ID URL, and to understand what's happening here, we need to look at both the view tree and the render tree. So the moment we add an identity modifier, our view tree is slightly different. It now has a new parent with the ID in it. And the ID, of course, is now initially logo.png. And the render tree, it's the same, right? Like a render tree also changes to include that logo. Now what happens is, let's say our URL changes. So the parent constructs a new view. Now it changed from logo.png to photo.jpg. That makes the entire render tree invalid. SwiftUI constructs a new view tree, and we can see here in the view tree it has photo.jpg, and in the render tree it has logo.png. And this is why I call it brute force, because what's going to happen is SwiftUI will remove all of the nodes from the render tree. So let's go there. So these will be completely gone. This includes any animations that might be running in any state. As you saw, the state is sort of stored in the render tree. If these nodes had any state associated with them, it's completely gone. So SwiftUI considers, basically, it removes all the subviews with any associated data, and then it inserts them again, but with sort of fresh data. For our purposes, this is really good. So the identity changed, the subviews are gone, or there's the subtree, and SwiftUI inserts new views. And we can see here that the task initially will be false again. So this is like a brand new task, a brand new Z stack, a brand new image. This is inefficient and often not what you want, but it does work for our case. But that's how you can do that. Now, how can we do it more efficiently? This is code, by the way. I wrote code like this myself and published it, and I've seen people writing code like this, and it's it's not bad, but it is like you have to be very aware of what's going on there in the render tree and how nodes basically get destroyed and any state gets destroyed and all of that. So how can we fix this? Oh yeah, first let's look at that this works. Let's say the task just appeared, did appear equals true. We have the new task. Now the photo.jpg loads and it updates the image data. And we have this new data, which means the render tree gets invalidated. So SwiftUI needs to re-execute it again. And now it has access to this new image data, right? And it constructs basically a very similar view tree. What you cannot see in this diagram is that in the view tree, we now have the new image constructed from the new data. And then it updates. And I think we should be able to see that this actually works. So it loaded once. If I tap it again, again, then it starts loading the image and like it goes back and forth. So all is good. Okay, now let's make it a little bit more efficient. So how do we do that? This is the code we ended up with the identity modifier. And let's go back to unappear because this technique actually works for both task and unappear, the ID modifier. When you have onAppear, you actually have the same problem. If you have any dependencies in your onAppear, it will not re-execute when those dependencies change. You need to be taking care of that by, for example, using the ID modifier. However, when you are using onAppear, you can combine it. And instead of the ID modifier, you can combine it with an onChangeOff. So what this will do is when the view first loads, it'll run the onAppear code. And then anytime that URL property changes, it will execute the onChangeOff. And this is a super useful pattern. And when I write onAppear, I always combine it with onChangeOff, or at least almost always, except if I'm doing something weird in onAppear that doesn't involve dependencies. In fact, this pattern has been so popular that people have been writing extensions that combine the two. So if you Google for onAppear or ChangeOff, you will find it. You don't need to Google for it. You can just write it yourself because it's very easy and you save yourself a dependency. So that's what the pattern you can use with onAppear. And like I said, when you do code review, I'm sure like everybody who has a code base right now, if you just search your code base for onAppear, I'm sure there will be missing onChangeOffs because this mistake is so easy to make. This is the new API that Apple just added to iOS 17. The onChangeOff now takes an initial Boolean, which runs basically in a way similar to onAppear. So it lets you combine the two into one. And this, unfortunately, it only works on iOS 17, so you have to write your own implementation, which is like 5 lines if you're targeting older platforms. Okay, that's all fine and good, but we had our task, which worked really well with async, and so we still had to use that ID, and the onChangeOff doesn't give us the async capabilities. Well, when task was added, Apple also recognized that this was a problem already, and so they have actually created a separate task modifier that takes an identity. And this is the identity for the task, which means that our image data gets loaded initially when the view appears, and then whenever the identity changes, it starts reloading that image data. And this solves all of the problems. So now we observe that change of the URL, as well as we're efficient. We're not destroying the entire render tree anymore. So this is how the render tree would look like identity is photo.jpg and did appear equals true. And then whenever that identity changes, SwiftUI will also re-execute this. This is sort of a side note. I've seen people writing these extensions, apply if. So what it does, it takes a condition and then it either like transforms self if the condition is true, or otherwise it doesn't transform self. And this is a very problematic extension, I think. Like people use it like this. Let me show you. So for example, they would write an async image with an apply if toggle, and then they apply padding if the Boolean is true. And like this feels very Swifty and like very modern, and it's also broken. If you recall what's going to happen with this if else change, it's a conditional content that will insert a subview and remove a subview. And in the render tree, this means that all of the state for these two subviews is gone. Like anytime the Boolean changes, the subview will lose all of its state. So in this case, with the async image will reload anytime you change this Boolean property, because it loses its node in the render tree. What you should be doing is not write these apply ifs, but because here you can see the view tree that we get, like the conditional content either has an async image or a padded async image. We should be writing it like this, where we set the padding to 20 if the Boolean is true and to 0 otherwise. And this is the associated view tree. You can see that if we translate, even if we translate this to a render tree, no views ever get inserted or removed. Now, this is not possible to write for every single modifier. A lot of the modifiers sort of have like a way to configure them to be a no-op. Not every modifier has that. If you can, you want to keep your view trees as consistent as possible and not have too many if-elses. I'm not saying like do not write if-else. Like you need those, but be aware of what it does to your render tree. And it depends a lot on where you use it. Like wrapping this async image in an if-else is not such a good idea. For other views, it might not matter. Okay, so we can see that our view still works. Let's see if we can load some more images. Okay, so we're almost done. But I promised I was also going to explain you a little bit about the layout system. And that's actually one of the problems with our myasync image implementation. Like it looks fine, right? And we saw the logo and we can see the photo. And let me enable the blueprint mode for the simulator. Now we can see that our photo stretches beyond the simulator. So this is problematic, it's wider, and we want to actually display the entire photo. And the problem lies in the layout. And so we're going to have a little look at that. Okay. This is the render tree that we ended up with. And to understand the SwiftUI layout system, it's actually really simple, but it has very complicated behavior in many cases. The simplicity is that SwiftUI always proposes a size to a view, and the view reports its own size. It chooses to either accept that proposed size, do something with it, or do something completely different. And in this case, almost all of these views in the view tree are layout agnostic. Like they don't really influence the layout system, but we'll focus on the more interesting parts in a little bit. Let's go through this once. Initially, SwiftUI will propose the safe area. So it'll propose that, let's say, to our myasync image. The myasync image will propose that to the identity modifier because it's layout agnostic, so it doesn't change this proposal. And this goes on, right? Like it's the same with the task. Task has no layout effect. In this case, the Z stack has no layout effect because it only has a single child. The conditional content has no layout effect, and now it gets interesting. So we're proposing the entire safe area to the image. Now the image says, okay, if you propose me 390 by 763, I'm actually gonna be 265 by 80. And that's, in this case, the underlying bitmap size. And then this reported size goes all the way back up the view tree. So to the conditional content, to the Z stack, to the task, to the ID, and to the myasync image. And to understand better what's happening here, we're going to just focus on only the image and see if we can make that work. So what's going on with images? When we proposed the entire safe area, we saw that the image says, you know, I'm only 265 by 80. And this is how it renders. When we propose, let's say 200 by 200, the image is going to say, I'm 265 by 80. So it seems like it's completely ignoring the proposal, right? When we propose nil by nil, which is the SwiftUI way of saying become your ideal size, or for the auto layout people, like become your intrinsic content size. When we propose nil by nil, the image again says, I'm 265 by 80. And image is not really configurable. it will always report its own bitmap size, which is, not what we want. Now, there is one way you can configure an image, and I think only one way, and that's by making it resizable. I do this as a single node because the resizable modifier actually returns an image. So this is like a single image node in the tree. Now, what does resizable do? Well, this is also very interesting. Let's say we propose the entire safe area. The image will become very big. It will become the entire safe area. If your designer ever wants you to make the logo bigger, now, if we propose 200 by 200, the image will actually say, I'm fine with that. I'll become the 200 by 200. So we can see here that image has these two behaviors, right? Like a regular image discards the proposed size, becomes the bitmap size, whereas a resizable image just accepts any size you propose, similar to shapes, for example, rectangles, circles, or what have you. Now, what happens when we propose nil by nil? Well, the image that's resizable is actually going to return its underlying bitmap size, its ideal size. Okay, and we can actually work with that. Now, as I mentioned, this is basically the only way you can configure an image. Either you have an image or a resizable image. There is no aspect image or something like that. There is an aspect ratio modifier. And the interesting thing there is that it works on any view in SwiftUI, not just on images. And it's like image doesn't know about this at all. So let's look at how that works. So this is what we can write: an image that's resizable with an aspect ratio applied to it. Now, what happens if we propose the entire safe area? Well, the aspect ratio first needs to figure out the underlying aspect ratio of that subview, in this case, the image. So how could it do that? Well, one thing you could do is you can provide a parameter there if you know the aspect ratio. And if you're like displaying things from the network, that if you can provide a parameter, that's great. But what if you cannot? Now, aspect ratio, I think, is very smart. What it does, it proposes nil by nil to the image. The image then returns its ideal size, 265 by 80. And then the aspect ratio takes that ratio, 265 by 80, takes the proposed size, which was our safe area, and fits a rectangle in there. And then it proposes again to the image. So it proposes twice. And this proposal is sort of this fitted rectangle. And now the image, it's a resizable image. It accepts anything we give it. So it renders exactly at its own aspect ratio, fitted onto the screen. I think this is a really cool technique, like how they implemented that. Like, it might feel very basic to you, but it sort of blew me away when I first saw this. So let's look at some other sizes. If we do 200 by 200, the aspect ratio again is going to propose nil by nil to the image. The image says, well, this is my ideal size. The aspect ratio then fits a rectangle inside that 200 by 200, proposes that to the image. And it looks like this. And see what we got here. If we have a photo, so I changed the image. It's a little bit hard to see on the slides. I changed the image to the photo. It's again the same idea, right? Like we take the safe area and propose it to our aspect ratio. Aspect ratio asks the photo for, hey, what's your ideal size? Here we have the photo, and we can see this really stretches beyond the bounds, right, of the simulator. The photo says, this is my ideal size. The aspect ratio then takes the proposed size, fits a rectangle inside, and proposes that again to the resizable image. And that's how the image now finally displays full width entirely on the screen, bounds to bounds. Okay, now this is our my async image, and we want to add support for resizability. We don't need to add support for aspect ratio because that's built into the system. One way we could do this is with a resizable property, and we could call it a day, right? You would just initialize it immediately, but yeah, let's at least make this work. So what we need to do here is we need to take this image and wrap it inside an if-let, an if-else. which is, exactly the thing I know I told you not to do, but the resizable modifier unfortunately only works like this. And this works if we want to have that nicer API. So if you look at line 9 and 10, we say image.resizable, like this is the way SwiftUI does it. If we want to have the same API, it's actually very easy to add that. So what we do is we make our property private, and then we can add an extension, resizable, and use the fact that our views are structs. So we just create a copy, set the property to true, and then return that copy. And now we have exactly the same API as image has. The real async image that Apple writes solves this in an even more flexible way. And that might be the way to go if you're actually trying to implement your own version. I just wanted to show this cute technique. Now we can see, I think, that it works, hopefully. Press the button and it resizes. So this is the old version, right? Where the image goes beyond screen. And if we now go to this new version, we can already see that stretches nicely. Saw the logo up there for a second. And yeah, this works. So that's how you can do that. I wanted to talk a little bit more about layout. So Paul asked me to see if I could extend my talk a little bit. So let's look at a few more small examples. This is a scroll view. Now, if you think about it, this is a vertical scroll view. This vertical scroll view has limited space horizontally, but it has a lot of space vertically, infinitely. And so this nil proposal that we saw with the aspect ratio is also used in scroll views. In this case, the scroll view will propose its proposed width, but it will propose nil for the height, so that the view can become and all of the subviews can become their ideal height. So this nil proposal is not like a cute thing that's used once, it's used throughout the framework and essential, I think. So this is how that would look like. This is a little bit of a fake render tree, but the scroll view starts by proposing, let's say 358 by nil to the first view, and the view responds I was 200, and to the second view, again, this nil proposal for the height, and then the view responds I was 80 high, and the third view, that view responds 400 in the final view. So none of these views know how tall the scroll view is. They only say if you give me nil, I'll become 80 or 200. And that's how the scroll view lays out its children. And this is also something to be aware of. If you put a rectangle, a regular rectangle in a scroll view, it will become 10 points high, because for shapes, 10 by 10 is sort of their ideal size. That's what Apple implemented. So if you have views that behave weirdly when you put them in a scroll view, it's probably because it's proposing nil in one direction, or if you have a horizontal scroll view, it proposes nil in the horizontal direction. That's something to be aware of. This is also really fun, the stack layout algorithm. There's a lot to it, and I can only cover a little bit of it. But let's say we have an ish stack with 3 views, a rounded rectangle, some text, and another rounded rectangle. If we render this, this is what it looks like. And if you think about it, how would you implement this, right? You want to make sure that probably the text is laid out, and then the other views, they need to stretch to fill up the entire available space. Well, with auto layout, this was easy, but how would you actually do that with proposing and reporting? I couldn't figure it out at first, even though I knew about proposing and reporting. And what's interesting is that it's not the order of the views. So if we would swap the order around, start with 2 rounded rectangles and then the text, it also fills up the entire available space. So let's look at what's happening there. I just swapped them around again, so we have rectangle, text, rectangle. This is the render tree that we get. We have a frame. I don't know if you remember, the frame had a height of 100, with the H stack, and then the 3 subviews. So the first thing that's going to happen is we're going to propose the entire safe area to the frame, 390 by 763. The frame had a height of 100 and no width parameter set. What it's going to do is going to take that 390, discard it, and use 100 for its proposal. So it's going to propose 100 or 390 by 100 to its children. So what the frame does, it both changes the proposal for the dimensions you provide, and it changes the reported size. Okay, so the frame is proposing this to the H stack. The H stack, well, it needs to distribute this space somehow. Like, how does it do that? And this is, again, I think, very interesting. The first thing that it's going to do, and I know there's a lot going on the screen, it's going to propose 0 for the width by 100 for the height. And this 0 is to find out sort of the view's minimum width. And it's going to propose this first to the first subview. And that subview, the rounded rectangle, says, okay, if you give me 0 by 100, that's the size I'm going to become. That's how shapes work. And I recorded that here in a little table. So the minimum width for the purple rounded rectangle is 0. Next up, the H stack is going to do the same thing for all of the other subviews. So it's going to propose 0 by 100 to the text. The text says, well, you know, I only need 84 for the height, but I can become that 0 width. So that's recorded in the table. And then finally, it's going to do it for the last subview. And that last subview works exactly like the first subview. And so it also has the 0 minimum width. Next up, and this is where my slides will lie a little bit, or where I will lie. Next up, the H stack is going to propose a very large value to all of its subviews to find out their maximum width. Because of reasons, I made it 5,000, but this is like, this is either infinity or greatest finite magnitude. And you can actually figure out whichever one of the two it is without looking at the source code. So the H stack is going to propose, let's say, 5,000 by 100. And now the rounded rectangle being a shape accepts that, so its maximum width is 5,000. Then the H stack is going to do the same to the text. Well, the text doesn't need quite that much space. So the text says, you know, well, if you give me 5,000 for the width, I only need 53 to render myself. So the text has a maximum of 53. And then finally, the last rounded rectangle is the same as the first. It also accepts at 5,000. So now we have our table complete. We have all the minimum and the maximum widths. And this is actually what the H stack does. And like I said, you can verify this for yourself. It actually will propose 0 and a very large value to each of its subviews. The reason why it does so is to figure out the flexibility of the subviews. And so we can see this rectangle, it's very flexible. Like, it will take anything you throw at it. Whereas the text is not very flexible. It's only 0 by 53. And the H stack is now going to order those views by flexibility. So it's going to say, you know, like this text was only 53 flexible. You can basically just take the difference of the two values, whereas the other two were way more flexible. They were 5,000 flexible. And the H stack is now going to propose an order of flexibility, starting with the least flexible view. And that's the text. And if you recall, I think the H stack had 390 proposed for its width by the frame. And now the question is, what is the H stack going to propose? Like, what is it? Is it going to propose 390 to that text? Or what if it's very flexible? Well, it turns out it's going to propose exactly the proposed width divided by the number of remaining subviews. So in this case, it's going to propose a third of the 390 because we have 3 remaining subviews. So here's our 390 visualized beautifully with a line. Sorry. Now, the first thing that H stack does is it's going to subtract the spacing. And so the 390 already turned into 370. Because we have 3 views, there's 2 spacers or 2 spacings in between the views of 10 points each. So that's why we end up at 370. Now the H stack is going to propose a third. So I added like a little visualization here, I think. Works. So it's dividing the 370 up into 3 equal parts. And that's why it's proposing 123 to the text. The text says, well, I only need 53, and the H stack takes the 370 that we had before, subtracts the 53, and now it has 317 points remaining. It has 2 views remaining, so it's going to propose to the first of those 2 remaining views, which is the rounded rectangle. And here you can see I divided the 317 up into two pieces because there are two views remaining. So it's going to propose half of the 317, which is 158, and propose that to the rectangle. Rectangles gladly will accept anything we throw at them. And so that's going to be the size of the rectangle, and finally also for the last rectangle. So you can see here that by starting with the least flexible views, this actually is an algorithm you can build on top of that whole proposing and reporting. And in practice, it almost always does what you want. Like there are many things in SwiftUI where that's not the case, but I think with stacks, typically they work, right? Like I don't know how many problems have, or how many people have lots of problems with stacks, but typically they actually work and they do what you want. And it's just by them being smart about this algorithm. Okay, so the H stack is done with its whole layout thing by proposing 3 times to each view. And it will report its size up to the frame, and the frame will report that same size back up. If the H tag would have reported a different height, let's say we only had text in the H tag, then the frame, because we provided a height explicitly, it's going to overwrite it, and the frame is still going to say I was 100 high. And now we're done, and this is why our view looks like this. So really think about this order, and you can also control this order with layout priorities and all kinds of stuff. And like you get groups instead of like a simple list that's ordered by flexibility. You can make this very complicated, and I'm happy to also explain that. But this is sort of the way things work. Okay. I can talk about this for hours and hours, but I'm gonna put an end to it. So I just wanted to mention, like, when we think about these trees, render trees or view trees, in many cases it's sort of the same. Understanding how your code translates to trees helps with understanding everything about SwiftUI. This is the environment, a little visualization. In the environment, the only thing that happens is that things get passed down the tree. That's literally all there is to it, to the environment. So each parent passes information one level down. And that's literally the only thing that the environment does. It passes information down the view tree from a parent to all of its children, no matter how deeply nested. I don't know how many people have used preferences. This is sort of the counterpart to the environment. The only thing that preferences do is they propagate the information up the view tree from children to their parents, and that's all there is to it. And here you can see like how 2 values sort of are combined. This is the reduce part of preferences. If you ever wrote a preference and you had to write reduce, this is what happens when you have 2 values that propagate up. And this is all there is to preferences. So again, it helps to understand what trees are constructed from your code. Yeah, and there are so many more things that I would or could talk about, but we'll really put an end to it. This is the book we're writing. We wrote this a few years ago. We rewrote it, and now we actually threw all of it out and rewrote the entire book from scratch based on the things we learned over the years by lots of questions, by giving talks, and especially by giving workshops where we interact with people directly. That said, we also do give workshops. If your team is interested, we do this only for in-house workshops currently, no public workshops. If your team is interested, contact me like either now or later or via email. It's really fun. It's like super intense, but it's also really fun to give, and we have a lot more visualizations. Here is actually the HTAG with layout priorities. You can see that there's different groups and everything, and it's nicer laid out than what I just showed in my presentation. Yes, that's it. I'd be very happy to take questions here on Zoom or also later after the talk. Thank you.
Hi. Hey. Yeah. So this concept of flexibility on the H stack, is this like a formal thing, or is this just a way of thinking about it? And does this mean whatever, if you had 3 texts that were 3 different lengths, that the larger text would be rated as being more flexible? And so like, but how formal a concept is this of flexibility?
I don't think there's any formal definition for almost anything I showed. The
There's a
place,
disclaimer at the start.
yeah, the place where you can find this back is if you actually go to there's an advanced layout session, I think the second year of SwiftUI at WWDC. And they explain this, like it's, I think, I think it was John McCall and Dave Abrams who gave that session. And they explained exactly what I showed you, but nobody, or almost nobody, I think, got that this is actually the formal definition. What you can do is you can log the proposals and the reports, and you will see exactly this. And it's not just for H stacks, it's also, of course, for B stacks. Z stacks are a different beast. And it's also for things like grids. With grids, the whole flexibility is in 2D, and there were all kinds of bugs in that. I was trying to figure out, I cannot figure it out. It's too hard for me. But with grids, there's also this concept of 2D flexibility, because they want to, like if you put very flexible things in there, like rectangles, you want to maximize the space while giving the other views enough space, and like, yeah, to log the proposals and the reports, what you can do is you can create, you can create a layout. I don't know, people know about like the layout protocol that's new in iOS 17 and macOS 13. The layout protocol allows us to write our own layouts, and it's the only place where we can use proposed size and reported size. And you can write a modifier that wraps a single view in a layout. And inside that layout, you have access to the proposed and reported size, and you can print those values. And you can just return the underlying view size. And this is a way to sort of debug that. And you can make this more complicated if you want, and like debug all kinds of stuff. But that's like one really great way to actually verify everything that I said. Because that's the other thing. I theoretically could have given the same talk after SwiftUI came out, because everything I said that I think is true now was true then, I think. The layout system has not changed, and the state system has not changed. But it might, right? Like none of this is formally documented, or like we don't know, like we have no clue. But yeah, verify it for yourself.
Great tip, thanks.
Any other questions? Yes.
I need to look up the name of this, but if you are integrating UIKit and SwiftUI, how do you take a UI controller representable and have it engage with this layout system?
So there is a hidden method, an underscored method that you can override. You need to find somebody who works at Apple who can help you with that. You can actually wrap it inside a layout and do something like that. I'm not too knowledgeable about the whole UIKit SwiftUI interop. Like my specialty is understanding sort of fundamentals of SwiftUI, and I consider that to be, like a minor detail. It's not, I know in practice, but for my, yeah. So the short answer is I don't really know. The long answer is that there's that API, and I've used it successfully myself. I don't know if it still works, but it worked. And then the other thing is that you can always add your own layouts to things. And that I've used successfully, well, both I think, to do like, I wanted to display attributed strings, and they needed to react to like different widths of the screen. Like actually the workshop app that I showed uses that technique to make sure everything works correctly when you resize the window.
I had found it to be non-obvious, and I'm glad to find it.
Oh, yeah,
It is in fact non-obvious. So
It's
in
not-
iOS 17, that type, the representable type, also includes a layout mechanism, which is equivalent to layout mechanism. So you can
Oh, yeah.
engage with the proposal, which lets you do it. I just wondered whether I was missing a trick on
No.
iOS 16.
No, this was not really supported.
Thanks.
Yeah, and another thing you could do is what we did before the whole layout story, and I think people know this, but you can do stuff with geometry readers and preferences and all of that. And now that we talk about it, like if you ever used a geometry reader and it did weird things to your code, the reason is sort of the price we pay for writing a geometry reader is that it always accepts whatever you propose. So let's say like you have an H stack with text and two rectangles. If we put a geometry reader around that text, that geometry reader will accept whatever we propose. So it will always become like a third of the proposed size in our example. And this is why geometry readers have this sort of bad rap. Like they're fine, but you have to sort of know how they work, what they do, and what the side effects are. And it all makes sense once you get it, but it's not really documented. Yes, go ahead.
I was gonna ask, with iOS 17 and like the changes with Swift macros and fate and observable and environment, does that make like that async image example easier in any way, or does it change anything around that?
Yes and no. So the new observable stuff is actually really simple, and it basically, in my testing, it actually does what you expect it to do. It feels like magic, but it's a macro, so you can actually look at what's going on. And mostly what it will do is like you will create a class, you will mark it as observable, and anytime anything changes in that class, SwiftUI will observe it for you. Regardless if you like use a state property or a regular property, it will just work, and it will re-render the view. Onappear and Task do not keep track of this. Like they don't use it, but you could write your own Onappear or your own task that does this for you, because you can hook into this whole observation mechanism. The only catch is that it sort of fires before the property gets set, so you need to wait to deal with that. Like it's perfect for SwiftUI, the new observation system, but it's useless for anything else, I think, because it's the will set. And so, like, let's say here you want to observe whether the URL changes. Well, you're going to get a callback that the URL will change, but you don't know the new value yet. So, like, of course, you can do stuff that I won't like say out loud, but you could totally make that work. It's not foolproof because it only works for the objects that are observable. The state property that we had, or regular properties, won't work like that. So it wouldn't work for this URL property in here. But you might be able to use it. I don't know, maybe at some point they will change how Onappear or Task works, but I don't really know. That would also have a lot of unexpected side effects. I don't think they can change it anymore. So yeah, it's a really good question, and I have no good answer, sorry. Any other questions? Yes, go ahead.
Is there a rule of thumb for when a node is going to be removed from the render tree?
Yeah, so when the parent's identity changes, when the parent gets removed, obviously, and like with an if-else, if the condition changes, and there's a bunch more things. Like if you don't write the else branch, but just the if, you have an optional node, and also an optional node in the render tree. And so if that condition changes and it becomes false, then that node gets removed. If you have an if-let, it's similar. And that's about it. There's very little dynamism in SwiftUI. You have your conditions like ifs and switches and all of that. You have for each, and you have any view, and that's the only three places where you can have sort of dynamic views. And you don't really notice that. Like SwiftUI feels very dynamic in some ways, but yeah, at those places things can be removed. It gets a little bit more complicated. Like one of the things you could do is have a list. Inside the list, you have a for each, and then you have all kinds of nodes in there. And I don't remember exactly the behavior, but it was something like the root nodes in that list. Let's say you have like a cell view. Those cells would never get removed again, like only when the whole view disappears, but then their children get removed. So state properties that were direct children of the cells, they would stay around, whereas state properties like, let's say, an async image in a cell, they would go away. And this has all kinds of issues. You want things to stay around because then, you know, like if the user tapped on stuff, you want to remember that. On the other hand, if everything stays around in a list, it's not going to be lazy anymore. So like, and people run into that when you have like images in your list and like your memory expands. And I tested it. You can test it yourself. It's not very hard to debug. But the problem is that there's no guarantee that this will ever change or stay the same. Yeah, and one other gotcha maybe that I forgot to mention. So I told you like don't put stuff in it, right? Like start loading stuff in Onappear. If you have, let's say, a list then the unappeared can happen multiple times. Like you scroll the view out and you scroll it in again. So unappeared might also still get called too often. Definitely not as often as init, but still, like, you need to be careful of that as well. I hope I don't make you sad, you know, like, but yeah, that's the unfortunate reality. Any more questions?
I got one more.
Yeah.
In the previous version of your book, when you use preference keys, you would do this thing with like color.clear to report the size.
Yeah.
Do you still have to do that now, or has that changed? Or
Yeah, so the general pattern we always used was, let's say, an overlay, and then inside a geometry reader, and then you have access to the proposed size. And so the overlay is very interesting. It's an overlay always receives the size of the thing it's overlaid on. So if you have like a text and you want to measure it, you do an overlay and a geometry reader, and the geometry reader receives the size of the text. And then you need to propagate the value up. And so inside the geometry reader, you cannot write preference. You need to put that preference modifier on some other view. And we always use color.clear. And yeah, that's still the pattern I use. I have no idea whether that's the best way to do it, but that's what we've been using all the time. In most cases, like, things have been improving, and so you write layouts these days, which can help you get rid of the preference-based layout. And there are just more modifiers that help. But if you need to target all the platforms, you will still need to use the technique, and it doesn't have to be a color.clear, but you will still need to have this like whole overlay geometry reader preference applied to some other view. It's just something, like, for me, it's just something I just type out very quickly and then sort of forget about it. You can write abstractions for this, but I find like it's okay that this hurts a bit, because you're going sort of against a stream, against a current. And like, it's fine if it hurts a bit to write it. If it's going to be too easy to write, I'm going to do it too often. And like, I don't know. I hope that helps. Thank you. Any other questions? Or do we have any Zoom questions? Otherwise, we can call it a day. I don't want to people back from the beers.
Right. Well, thank you very much.